Well, welcome everybody to the CSE seminar this month. I'm very pleased to welcome Professor Georg Stadler from the Courant Institute at NYU. Georg is a professor of mathematics and computational and computer science at Courant. And before joining NYU, he was a research scientist at the Odin Institute in UT Austin for many years. And before that, he received his PhD in mathematics from the University of Graz in Austria. And Georg is really well known in PDE-constrained optimization and inverse problems and uncertainty quantification, and has worked on a variety of kind of engineering and science applications, particularly geophysical applications. He's won the Gordon Bell Prize at supercomputing, and he's won the 2019 Computational Science Engineering Best Paper Prize from SIAM, among many other awards. And really pleased that he could visit us, so to speak, today. And while this is a virtual visit, maybe there'll be future in-person visits too. So we're very glad that Georg could spend the time today. Please take it away.
Okay, great. Yeah, thanks so much. Thanks for coming and thanks for having me. I know there's like so many online talks these days, so I appreciate that you come to this one. So my plan is to talk about something that many of you actually, or some of you I know, are actually working on similar questions. So it's about estimation of small probabilities, so extreme event tail probabilities. And in my case, it's going to be in complex systems governed by PDEs. And I'm going to explain what I mean with this. So this is mostly work by Shanyin Tong, who's my student. She's co-advised between me and my colleague, Eric Vanden-Eijnden, whom I think many of you also know. And so she has done the hard lifting on most of this material. And okay, so let me jump into it and try to, so this is an overview. So I'll first try to explain it in math terms, and then I'm actually going to give the driving physics example and explain a little bit why we care about this problem. So the math problem is the following. So the estimating probabilities is the basic framework is the following. We're gonna consider a map F, which goes from a possibly high dimensional parameter space. So theta is going to be my parameter, and I have to apologize already. So I sometimes call my parameters theta, and I sometimes call them b. So theta is my generic name of my parameter vector. Okay, and when I talk about the application, which has to do with Tsunamis, I sometimes call it b. So theta and b, same thing in my talk. So I'm assuming that this is a parameter, and it comes with a density, with a distribution. So this is a random space parameter. And I have a map from this possibly high dimension parameter. That map F goes into R, and that map F is the parameter to event map. And in my case, I usually this is a complicated map, so it involves usually a PDE solve. It could involve anything complicated. The main thing is it's expensive to evaluate, right? So it's not something that you can do 1,000 times in a second. It might really require solving a couple system of PDEs. So you can talk about minutes, maybe even hours. So it's a complicated map. So because in general it involves a PDE solve, which we know takes a while. And in the example I'm going to talk about this is going to be the solution of a time-dependent shallow water equation. So the time-dependent hyperbolic equation. It's only in 1D in space at the moment, so it's not that expensive. But you can imagine you still have to time step it, and it's quite expensive. So that's this map, okay, and it maps parameter values, okay, in an n-dimensional space, right, with a distribution. It maps these into like a one-dimensional distribution that's drawn here. And so these are actually samples from distribution, and I'll often my cartoons will often be based on nice looking Gaussian-ish kind of distributions. This would be a two-dimensional parameter distribution here, but most of it doesn't need to be Gaussian. So while my cartoons look at this, it doesn't have to be Gaussian. Most of the time, I'll mention a few things. There are certain restrictions, but in general, these are just my sketches. And what I'm interested in, so we're going to map from this distribution in n dimensions, right, into this one-dimensional thing, and we're interested in quantifying the tails, the probability to end up in a tail of this distribution. So we're interested in trying to find the events, right, which are kind of samples here from this distribution that get you after this complicated nonlinear map, that get you in the tail, and then we want to estimate the measure of those distributions. So you can think of it, let's say all the points, right, that would lie out here, they would lead to this random this red tail here, right? So they would map you here. Then we'd be interested in computing the measure, like the probability of this set. Okay, so the target is estimate the measure of the extreme event set for some z. So this extreme event set, omega z, is defined as all the parameters theta, such that f of theta is larger or equal than a z. So they give you something larger than a threshold. Here would be z, but that's the extreme event set for a specific z. And you can imagine if you make this set larger, right, then this extreme event set becomes smaller. The sets become the events become more extreme, and there's fewer parameter values that lead to these events. So this is, we want to either measure compute the measure of that set, right, or equivalent, just compute the probability of that after you apply this mapping f, that you end up with a value that is larger or equal than z. But that's kind of the same thing. So that's in general what we're interested in. So again, just repeating here. So we're interested in this event set, right? And the larger z becomes, right, the more extreme, the more unlikely my events get, and the smaller this probability becomes. Okay, so this is again the same sketch here. So I'm saying for a specific z, this would be all the events that lead to all the parameters that lead to an event of magnitude z or larger. So we want to measure to compute the measure of this set. And if you increase this for a larger set, right, you get a different event set. It's contained in this previous one, but this might be omega of z2, right? If z2 is larger than z1, let's call this z1, right? So, and that there's a subset of that leads to these more extreme events. As you probably know, the more extreme and rare such an event is, then it becomes typically more difficult to characterize this probability. And this is even more the case, right? If valuing f for a parameter theta is expensive, right? Takes time on the computer, is an expensive thing. And if theta is in high dimensional space. So my sketches are in 2 dimensions, so there's 2-dimensional parameter space. But if you are in higher dimensions, as we know, anything that has to do with probability becomes much harder if you go to higher dimensions. That's often referred to as the curse of dimensionality. So then things become harder. Examples of these things, right? What are these? Why we care about small probabilities if they're small anyways? We care because we care in the cases where these events are low probability but very important. Okay, and examples for these are something breaks, so it's material failure. You have extreme weather patterns like hurricanes, tornadoes, right? They don't happen too often, but if they happen, they're very expensive. You have wave phenomenon. So I'll talk about tsunamis here. Rogue waves are another wave phenomenon that plays a role here. Extreme turbulence behavior. So all these unlikely but very important events. Or in the financial sector, you have you can also have these crashes or something that happens, but when it happens, it's very expensive. And I should have mentioned it. I think we should add pandemics here. As we all know, doesn't happen very often, every couple of 100 years or so, but obviously very, very high impact. So that would be another example for something useful to say something about it. Might be hard, but it's one example for these low probability but high impact events. What's common to all of these? Common to all of these is they're rare, but they are very expensive. And we want to make it makes a big difference if a probability of an event is like 10 to the minus 3, which is small already, right? Or 10 to the minus 7, right? If you think in terms of an insurer, that obviously makes a huge difference, right? In terms of how easy it is to insure some event for an insurance purposes. And I'll use as my main story. I'll use tsunamis here, but a lot of the stuff I'm talking about is somewhat generic, and I'll talk a little bit about what you need for this function f to apply to different concepts. So I'll try to make a connection between estimating probabilities and optimization. And I also want to point out that in general, that's not a straightforward connection. And the way I think about it is, again, there are exceptions to this. I'm overgeneralizing it, I'm aware of that. But the way I think about this is anything with probabilities is typically much harder than doing optimization. Okay, so at least if there's certain smoothness, optimization I know how to do in high dimensions, maybe even infinite dimensions, right? So that's fine. If you do anything with density estimation, probability estimation, it becomes very hard with increasing dimensions. So in general, these are really kind of two different things. And the question is, when is there a connection? When can you make a connection? So if we talk about a probability, one thing we can compute is we can compute the maximum likelihood point of a density. So the most likely point in a density, but unfortunately, so if you think of again 2D, right, you have contour lines of a density here. The most likely point would maybe be somewhere here, right? And that's something you can compute through optimization. But it turns out most of the time that point is actually statistically not very interesting, not very important. Okay, so in terms of overall probability, that point is not really that important or that useful. Okay, it gives you some information, but it's not really that useful. So this is what I already said. Optimization is typically doable in high dimensions. High dimension statistics is hard. It suffers from the curse of dimensionality. So that's it. So the question is, when can you use optimization ideas for probability estimation? And the argument is you can use it in a certain limit of extreme events of rareness, that you can actually that somehow the probability estimation problem becomes hard from one perspective, but when you take this optimization perspective, you can actually make it easier, or you can compute reasonable approximations. Okay, so the main takeaways, and that doesn't mean I'm done yet. I'm done. So this is just beforehand already. So I will try to illustrate in this example that these kind of methods that are these methods to estimate these extreme events or rare events that are mostly insensitive to how extreme the event is, so how rare it is. Okay, so it doesn't. These methods typically don't degrade or degrade at a very slow rate as you become the probability becomes smaller and smaller. The goal is to have something that works in high dimension parameter spaces and for expensive maps F, right? As long as these Fs I can compute derivatives. So I will need derivatives of this map F. I'll make a connection. There is to what's called large deviation theory. That's a theory from probability that allows us to do some mathematical, pretty rigorous arguments when this actually applies. Okay, so it's not generic. It's not always going to work. You can break it, but we have conditions such that we can say when this works. And that will allow us to argue this connection between optimization and probability estimation. And because I'm interested in problems where F involves the solution of a partial differential equation, it's a very specific kind of optimization you get here, which is sometimes called PDE-constrained optimization. So that's optimization where you have constraints given by PDEs. So this will end up with problems of this structure. It's going to work for nonlinear parameter to event map F. And these parameters, theta, and sometimes called them B, right? They can be Gaussian or non-Gaussian. Everything is, of course, hard in a non-Gaussian way. In general, they don't have to be Gaussian. And I'll illustrate this with this application of these Tsunami event problems. Okay, so that was kind of the over the mathy or CS&D overview. Now let me come to the application I'm interested in. So this is with Tsunamis, and I'll quickly remind you what causes Tsunamis. So what causes Tsunamis is the following. So you have basically it's plate tectonics. Okay, so and plates push and rub and there is plate subduction. So one plate gets pushed underneath another one, and that happens at a very slow rate. So a couple of up to 10 centimeters per year, and over time it builds up stress in the overriding plate. That's this plate here, right? And then if the stress is too much, right, there is like a sudden slip of the plates against each other, and we experience an earthquake. But more important for Tsunamis is that at the same time, the ocean floor gets lifted or pushed up and down in some irregular pattern. So this is in this cartoon, it's lifted, but in general, it's somewhat an irregular pattern that lifts the whole water column above it. Okay, and then the lifted water column starts to travel as water waves, and after, depending on the distance, right? These water waves, they travel to shore, travel in all kind of directions, right? And then while they travel, they interact with the ocean floor, right? And then on shore, half an hour later, an hour later, 2 hours later, depending on the distance between the shore and the event, right? We experience a tsunami wave. That means it leads to very strong flooding and all kind of expensive and loss of life, of course. So that's the main mechanism. So it's caused by this by this sudden rupture, sudden movement of the Earth crust, right, and the lifting the water column above it. That's what it says. And these waves, obviously, as we have seen, unfortunately, several times over the last decades, they can travel hundreds of kilometers and lead to severe flooding. So that's the basic mechanism. If you look a little bit in more detail, so what is this map showing? So this is the up and down lift that resulted from the 2004 tsunami after the 2004 earthquake in Sumatra. Okay, so what you can see is in the red areas, the ocean floor, so the up and down lift of the ocean floor gets lifted up by up to 5 meters. So it's quite up to 5 meters, and the blue areas, it's actually going down, in this case, up to 2 meters. Okay, so it's a complicated pattern of up and down lift. And in general, you can't really predict this pattern, right? Because you can't predict where the rupture occurs, and then there's always like patches. So the actual slip, right, occurs under the ocean floor, and on the ocean floor, that's the resulting up and down lift of the ocean floor. Okay, and that lifts up and down lifts the water column, and then the wave starts traveling towards shore, could be in this direction. So you can see it's a couple of meters, 2-3 meters, but the main problem is that these are huge areas, right? This can easily be 50 to hundreds of kilometers, right, in size, right? And then as these waves travel, they interact with the ocean floor, and they get actually compressed in shallower regions. So if it starts out as something that is just 1 meter high on average, it's gonna build up when it gets to shore and becomes much higher, and then that's why it leads to severe flooding. So that's the source that starts this a tsunami wave in general. And you can see this bathymetry change. Let me remind you quickly. So bathymetry is the depth of the ocean. So the rock at the bottom of the ocean, that's called bathymetry. Okay. So bathymetry is the same as topography. Topography is outside the water, and bathymetry is the name for it inside the water. I think that's the main. And I think the sign might be different, but topography is plus, and I think bathymetry has a negative sign. But basically, that's what I mean with it. And this is smooth, but it can be very complicated. So it's hard to predict this thing. So what I'll do for my purposes, I'll model this bathymetry change as a random parameter field. Okay, because I don't know it. So I'll model as a random parameter field. And so here is again a sketch of this is actually in front of Japan. This was the Tohoku earthquake in 2011. And here's just a slice again. So here you see the ocean depth, right? That trench, the dark blue area here is where it's very deep. And this Pacific plate here, so we switch to a different color. So the Pacific plate here is this plate, and that moves at a rate of 8 to 10 centimeters a year, I think, in this direction, right? And it gets pushed underneath this plate here, right? And then once it slips a little bit, right? Then that's when you have an earthquake, and at the same time, uplift of the ocean floor and the tsunami wave. Okay, and actually, in this case, the problem is this is actually fairly close to shore, right? So that's why Japan has invested so much money into tsunami warning systems, because they don't have too much time. So when something happens here, I think the waves are there in like 15 minutes or something. There's not a lot of time for people to get on in higher ground in general. So if you slice this region like this, okay, so it looks kind of like this. So you see here again the Pacific plate here that's being pushed underneath it. The slip occurs somewhere in this region, right, and results in some kind of uplift of the ocean floor somewhere here. Okay, and yes, that's the mechanism. And my toy problem will also be one-dimensional, and I agree that's very simplified. But the two-dimensional shallow water question would be actually way more interesting. But so we're working on that. But I'll use this as kind of this geometry as my inspiration for my computational geometry. Okay, so here, by the way, here are the towns, right? Somewhere here is Fukushima or something. That's where these things happen. And I work with a domain that looks like this, right? So it's inspired by this. It looks similar. You see here distance to shore. So here the slip is around 150 kilometers away from shore. And in these regions, you will get some random up and down lift as a result from the earthquake, from the slip. And the governing equations is the equations for tsunamis are the shallow water equations. So that's this equation. In 1D, the equation looks like this. So it's a hyperbolic conservation law. The variables are the height of the water column and the velocity. Okay. and it's nonlinear. So if you look at, so this is linear here, but this here you see nonlinearity. So you have these terms like this. So there's a nonlinear effect and that's also the effect that leads to steepening of waves. And I'll show this in the next thing. So there is a nonlinear hyperbolic conservation law, and that's what is the F I was talking about. So the F starts basically the theta, this parameter theta or B, right? This random parameter that is this bathymetry change, right? How does F map it to my observation? And I'm actually going to observe the water height in these red regions, and it maps it by the solution of shallow water equation. Okay, so this change here is like an input on the shallow water equation. It's actually this B here on the right-hand side. And then you have to solve a time-dependent, and in this case, 1D in space and 1D in time equation. And after some time, this wave hits shore. And so the map F, the kind of complicated map, right, is exactly, you get it by solution of this 1D shallow water equation. Okay, that's the map. And you can imagine that takes a little bit of time to do this. And so here is just a simulation of a very simplified simulation of what this does. So if you have a very simple uplift here of that water column, and it's also plotted in larger than it actually would be here. So this is the same region. The wave would start here, and this is just the zoom in up here, right? And then the wave starts traveling to both sides, right? There's like this, okay? And then as it travels, it changes its shape and interacts with the ocean floor. In this case, it's a simplified thing. In practice, it can be much more complicated. So what you can see is becomes steeper and narrower, right? And also like because of this, the nonlinearity of the shallow water equations, the front here becomes actually steeper. So this is, you get steepening here, and you can have what's called shocks. That means that the slope of that wave can go to infinity, and you need computation that causes all kind of troubles, and also like theoretically actually causes troubles. So you can see these waves. We don't care about the right wave that much, but the left one, and it travels to shore, right? And then when it gets to the red area is where we're going to observe the water height or the average water amount there, and that's when we measure it. So that's when we measure how extreme our event is, how large this quantity is. And you can see that the wave has interacted with the floor, so there's going to be some kind of reflection here. So that's what's going on here, and so there's some nonlinear, non-trivial interaction. Okay, this is like later in time. So here it took 1800 seconds. So these are physical units. So this is how long you have from in Japan until the wave, the first wave hits shore, roughly. Okay. And I still need to tell you, so I told you a little bit what the parameters are. This is bathymetry change here, and I told you what the physics is, but I have to tell you now how I measure my F, right? So what's going to be the measure for my extreme event, and what it's going to be is I will, in this red region, I care about the additional water height. So the additional water height is the water height plus this is the reference bathymetry. So this is a negative sign. So this is just the added water height due to the tsunami, integrated over these red regions from C to D, and I care about it. I don't know exactly when it's going to go there, so I care about it at any time when it's the largest. So I maximize over all times. So that's my measure, right? So my measure will be for random bathymetry change here. I have to solve the shallow water equation, and then I compute this quantity, and that's the thing I'm interested in. This is a measure for how much additional water height or water mass is in this region close to shore, and that's kind of my measure for how extreme how bad the tsunami will be. And there's a max here, and that makes, because I will need derivatives of this F with respect to B, the parameters, again, B and theta, the same thing. There's two ways. Either you keep the max and you end up with optimization problems that have time optimal control problems, or you smooth this max over time, and this is the smooth formulation. So believe me, so this for gamma to, I think, 0, this goes to this maximum here. So this is just a technical issue how to do it, but that's the quantity I'm interested in. And then, okay, so this is just the setup. So this is just, again, showing where the slip occurs and how complicated these slip patterns can be. So this is my justification to say I want to model this as a random parameter field. Okay, so now let me summarize quickly a little bit about this, the theory behind this. So, so as I said, right, I'm interested in measuring the probability or estimating the probability of this event. So estimating the probability that the outcome of my physics is larger than Z, given some distribution, some distribution which I'm going to model for these parameters. Here, I write down a normal distribution, but it doesn't have to be normal distribution. In principle, it works for other ones as well. And so where can what's the theory that brings optimization to these kind of problems? And that's kind of an adaptation of large deviation theory, which is a very theoretic theory in probability. And we are just using that framework, but we're not directly applying it. So we just using that notion and stuff, but it's not a straightforward application of that theory. Okay, but we're just using that the things that one can learn from large deviation theory. Okay, and basically it's a theory that tells you something about the tail behavior of distributions, and that's kind of what we're interested in here. There's a little bit of a technical difference. Usually when you do LDT, you keep the set kind of constant, and you change the probability, the probability density. In our case, we keep the probability constant and we move the set. So the perspective is slightly different, but we borrow these ideas. And this whole combination of trying to use optimization to estimate probabilities, that's not a completely new idea. This is used a lot in thermodynamics and statistical mechanics. And several people have actually used this connection on some or the other level before, including Tsunamis, who is actually at MIT. And other people have become also interested in estimating probability of low probabilities in complex systems. So there's definitely some work out there. Okay, so now this is this connection now formally between large deviation theory and optimization. So again, we're interested in this set, right? The set of parameters that lead to these extreme events in this set and its probability. And the connection is that this theory tells us that that with this this underlying probability, we can compute something called what's called the rate function. Okay, so that's a convex function that depends only on the probability. Okay, and for simplicity, so that can either be computed analytically, and sometimes it can only be computed numerically. But for simplicity, I assume that my underlying parameter distribution is Gaussian, and then the rate function is very easy. For Gaussians, the rate function is just the log likelihood. So it's just this. It's the quadratic part that defines a Gaussian in high dimensions, right, or in n dimensions, where this is the covariance matrix. C is the covariance matrix in a precision matrix. So for Gaussians, it's just a quadratic term. For other things, this rate function is still convex, but it's possibly more complicated. But for now, let's just do Gaussians. And then this theory tells us that the connection is the following. So we want to solve an optimization problem, and the optimization problem is you minimize the rate function, okay, over all the parameters that lead to this get you in this set, that are in this set omega c, that lead to an event of size z or larger. There's a sketch on the next thing to illustrate that, but that's the optimization problem. That's the problem that connects the probability estimation to the to optimization. And I'll sketch on the next slide. And then what the theory tells us that these minimizers, right? B star that depends on the Z, right? These minimizers actually give us a lot of information about the probability already. So this is just a point. So that's the kind of interesting thing in my perspective. It's just a point of that large set, right? We're interested in the measure of that set. And in general, I try to make this argument that just having a point it doesn't tell you much in terms of probability, right? But in this case, this point is actually quite useful for probability. And in specifically the probability, you can show that the probability is some prefactor, and it's all going to be about estimating that prefactor times e to the rate function, and you just plug in this point you computed. So you have to solve optimization problems. You get that gives you this factor, and then all that's left is to estimate this prefactor, and that's sub-exponential. So that grows. Most of the growth in this thing, and then this prefactor is kind of a correction to that probability. So in a sketch now, so this is again the blue lines are now these contour lines, the level sets of that rate function. These are the blue dotted lines. And for a specific Z, this is the extreme event set. So we want to estimate the measure of that extreme event set. And the LDT tells you, this large deviation tells you that just having this one point here, that is the most likely point if you compare with in this extreme event set. That's already some very useful information, in particular in the limit that Z becomes large, which means that this set moves more and more out there. Okay, so that's kind of the I think cool thing. So this point actually tells you a lot of information already, and that point we can compute. Okay, and then you need this point, and then you have to estimate the prefactor to make it more accurate or even exact, right? But that's the whole theory. So that's kind of the basic connection. And so in practice, you would do several Zs and you compute these points several times, right? And they tell you something about the behavior of this rare probability. Okay, so to make this connection rigorous here, this is just a sketch of the arguments that go into the proof. So what do you need at least? So you need definitely differentiability of f, right? This map needs to be differentiable, and I actually need to compute gradients. And for one of the methods I'll show you, actually need second derivatives as well. You need certain regularity of the probability function, okay, such that some density is well defined. You need that this minimizer, right, that actually has to be a unique. That's probably one of the strongest assumptions. So you need that this minimizer, this one needs to be unique in that set. Okay, so that doesn't prevent you. That's still okay, right? If that set could still look like this, right? That's totally fine, right? Because this is still going to be the most likely point. But if you have not unique points, or if you have multiple minimizers, then this thing won't work. That's some of the strong assumption, but in practice, I think it's not unreasonable to do this. And then you need a certain regularity of the extreme event set, but these are all, some of these you can check at least after the fact. So these are all, these are basically the assumptions that you can make these arguments rigorous. And why are these nice, right? So here I just copied the problem again. And actually from these assumptions follows that you're not only looking for this point in the set, you actually can show that this point is the point needs to be on the boundary of that set. And that's also what the sketches in my previous slides showed. And then because it's on the boundary, that means that f of this b is equal to z, right? And then this means that you minimize a function, that's a convex function, I of b, the weight function, over this condition, which is a kind of a constraint that involves a partial differential equation. And then you end up with you can reformulate problems like this often as minimizing as unconstrained problems. So you minimize something that is the rate function minus some lambda, that's a fixed number in this case, times this f, okay? And then you end up having to solve problems that look like this, that are minimizing some objective, and you still need to solve the shallow water equation. So this is now this PDE-constrained optimization problem. So you have to optimize something, but it's constrained by the shallow water, the physics, the complex system physics, and that's the shallow water equation. Okay, so that's why this is a PDE-constrained optimization problem. And this looks a lot like what you know when you've worked in, for instance, deterministic inverse problems. You have to solve problems like this all the time. Okay. Now let me show you. So this is the formulation. So we have to solve a bunch of these optimization problems. So I want to talk at the end 2 minutes maybe about how to solve these optimization problems, because they're quite interesting from an optimization perspective. For now, I just want to show you what you can do with these things. So so when you try to use sampling for these to estimate these probabilities, okay. So when you just try naive sampling, which means you just you take random draws from this distribution of theta or b, right? And you just compute f of theta and b, and then you see where you end in this one-dimensional probability. If you just do this, the main problem about this, and it's the general problem about estimating any kind of low probability, is that you get estimates up to a certain. So this was standard Monte Carlo method, and I think it was 10,000, 100,000 samples actually. So you get decent estimates up to a certain point, and then you get so few samples that actually end up in this extreme set, right? That your error estimator just blows up. So you cannot see anything about the behavior in this regime, right? You cannot basically you can't say anything about probabilities that are below 10 to the minus 5. Okay, so that's the main problem. And what this theory gives you is that if there's this prefactor, and if you assume it's a constant, okay, so that's wrong in general, as I'll show you. But even if you do that, then that gives you some estimate of the probability to way lower probabilities, right? To explain, this is the probability here on the y-axis, and here is the extremeness of the event, right? So out here you have less likely events that are more extreme. Okay, so then that gives you at least some rough estimate, but you can do better than that. So you can actually do a very simple shifting of this probability, and that gives you a very basic importance sampling technique. So instead of doing these random samples here, these blue ones, right, you can kind of shift that and then correct for that shift. That gives you these green samples, and you can use this actually to estimate the probability here. That's an improvement, a significant improvement. It's also a known method. And why is this an improvement? So if you don't do that shift, right, if you do it a very naive way, which really one shouldn't do, you get that the relative root mean squared error of an estimator for this probability looks like this. So it has terms, n is the number of samples, and it has terms, it has a term that grows exponentially. That grows exponentially with the extremeness. So that's the term that's going to make it very hard to do this. Okay, so and the 1 over square root of n is the typical Monte Carlo estimated error. But you have additionally have this term that becomes very, very bad, very large when z grows. By doing the shifting, you basically get rid of this term and you end up with something like this. So you still have the Monte Carlo 1 over square root of n error here, but this constant is almost independent from z, so that's actually much better. Okay, but that's not the main method I want to promote. So this is, if you do this right, so you end up with you can estimate you can get pretty good estimates of the probability in this very low probability regime. And what this amounts to, right? You basically have to solve for multiple sets, right? You have to solve optimization problems here, for instance, right? And then with this estimate around that optimization problem, you do this importance sampling, and that gives you then a pretty good estimate of the prefactor. So that's one useful way to do this. But what I actually want to show more is the other idea is that, so we again back to this problem here. The thing I want to talk a little more about is you can actually do another thing. You can compute this optimized at this one point by solving an optimization problem, and then you use local curvature information around that point to compute this prefactor, and thus an accurate approximation of this probability. So what is this based on? This is based on doing estimating this boundary locally with basically a Taylor expansion. And in engineering, these methods are also kind of known. With a Taylor expansion, and that gives you a quadratic approximation or a linear approximation of that set, right? And then with that information, you can actually you can get an improved approximation of this prefactor. And so this is the computation it needs. And the interesting part is, so my sketches are in 2 dimensions, but I'm interested in problems in higher dimensions. Okay, so you need information about the local curvature at that point. And if you're in high dimensions, there will be many directions. But the interesting thing is, you only need information about the curvature at this point in which the curvature is not close to 0, which means it's not flat, because that has an impact, right? So it's about the local geometry of this set. So you need where it's not straight or not close to being straight. So you need that. And you need it only in directions where the underlying rate function, that's these blue lines, is important, right? So basically you don't need to explore the geometry locally in directions where either it's almost flat, the set is almost flat, or the rate function is or then are not important for the probability. There's no probability mass there. Okay, so only in those directions you need this information, and there are ways that you can efficiently compute these things. And these ways are laid out here. So what you basically need is, so this curvature information is second derivative information of this mapping F. So in this case, you need F to be twice differentiable. Remember, F involves the PDE solve, okay? So non-trivial thing. But you can actually then just explore, you don't need this whole second derivative matrix, because that would be very hard and expensive to compute. All you need is, you need the eigenvalue directions in that matrix that are important for that matrix and important for the underlying rate function. And those you can actually compute quite efficiently using, for instance, a randomized SVD method. So you can compute these just by applying this Hessian, which we know how to do from PDE-constrained optimization, and the covariance matrix from the underlying probability. Okay, So you can very easily explore this local geometry information, and that allows you to compute an accurate approximation of this prefactor. And this is one of the ways that you can compute this. But so this method, engineers do some version of this method without these randomized ideas and without in lower dimensions typically, right? That's called second order reliability method. Okay? So the idea is just to kind of make it work in higher dimensions and exploit that. You don't need to know the secondary matrix completely. You just need to know it in some directions, because these directions contribute to this correction factor that you get here. And if you do this, you can actually get this red there. Estimate these low order small probabilities, and it's much more accurate than with other methods. Actually, this is a comparison. So here, this is always dominated by this exponential decay factor, right? So it's hard to compare different methods here. So what we do is now we take out that factor, right, and only compare the prefactors. Okay, and if you do this, you can see the following. So the blue line is the MC, the naive way, right, which you basically can only use it up to a certain point. Then it becomes variance, makes it useless. Then there is the important sampling method, and this important sampling method, we know it has a Monte Carlo error, but we know it's actually in the limit of n, it's actually gives you the exact probability. Then there is the second order where you use this local geometry information. That's the red line, and you can see asymptotically these are actually they perform very similarly, and you can actually show that for both of them. For the green one is asymptotically exact for n for any kind of z, for any kind of extremeness. But you can show for the red one, that's the second order approximation, that's at least asymptotically exact. So if z goes to infinity, the probability becomes smaller and smaller, then this quadratic approximation becomes actually exact, and you can analytically prove this. If you just use this first order approximation, that you don't take into account the local curvature, then it's known that it's not asymptotically exact. So you can see this factor is really there's a significant gap in between here. So that you need to use this local curvature information at the point to be at least asymptotically exact, and that's what these red dots are doing. Okay, so quickly, this is a more realistic setup where we're trying to use these methods now to actually really say something about the physics of tsunamis. So it looks similar. We've a more complex slip area now. Then what we do is for the previous stuff, actually, we modeled these slips lead to some bathymetry change here, and we modeled the slips as Gaussians, but that's actually not a realistic setup. So now we model them as a mixture of log normal distributions. And this allows us to, and what we do is actually the log normal, you transform a Gaussian, and we actually move the transformation into the mapping F. So it still allows us to work with several Gaussians now, but it still allows us to use similar tricks, because we move this transformation, we move it in this map F. So there's some modifications there. And then these are the random samples we would get from the bathymetry change. We actually set it up in such a way that we get the same behavior that we know from earthquake magnitude. So we make sure we have over a range of Richter scale 7 to 9. We actually get our model actually gives us realistic probabilities for earthquake magnitudes as well. And then you can ask questions about which. So it's a mixture of Gaussian. You can ask questions like which of these mixtures contributes is the most important for having a flooding event, a wave size, right, of 3 meters onshore, and what's the most effective mechanism for an earthquake, right, to produce a tsunami of a certain height, 3 meters in this case, onshore, in each of these mixture models. So basically, we're trying to just bring this in a physical setting where we can really say something about what the mechanism is that leads to these tsunamis and how likely they are. But I want to spend like 2 more minutes, because I think there's a whole set of quite interesting mathematical optimization problems that originate from this. So I want to spend like maybe 2 or 3 minutes talking about these PDE-constrained optimization problems that show up in this context. So I told you, right? We have to solve there's several solves of these optimization problems that we need for large deviation theory here, for using this, making this connection. And they're all of the form, we minimize something convex minus, this is this measures how extreme the event is. And it's always subject to the dynamical system, the shallow water equations in my case. Okay, so it's a PDE-constrained optimization problem. And this method I showed you, the optimization itself needs at least gradients of this problem, right? Because otherwise I usually can't really solve an optimization problem. And then this second order method I showed you needs actually even Hessians of this objective with respect to the parameters, which is B, right? And obviously when you want to compute gradients of this objective with respect to B, you have to take into account that there's always constrained by this nonlinear PDE. So you have to you need what's called adjoints and second order adjoints to compute first and second derivatives here. So let's talk a little bit about these constraints. So these are the shallow water equations in my case, right? If you have a different physics with different equations, in 1D they look like this. Okay, this is the shallow water equations, and to compute the gradient of an objective that's governed by the shallow water equation, you have to solve what's called adjoint shallow water equation. So this is the efficient way to compute such gradients. I'm sure many of you know. And you have to compute these adjoint shallow water equations that look like this. They're again a hyperbolic system. It's actually a linear hyperbolic system, but it's a non-standard. This is a kind of a non-standard hyperbolic system. So each time you want a gradient at a certain point in the bathymetry in the parameter space, you have to solve the corresponding shallow water equations. Then you have to solve adjoint shallow water equations, whose solution depends on the forward shallow water equation. You compare them, and then you can compute a gradient, and that's the gradient you compute. Okay, so that's the thing how to efficiently compute gradients. And with similar ideas, you can compute second derivatives, but you cannot compute the second derivative matrix directly. You can compute applications of the second derivative matrix into a directional derivatives of that. So it's directional second derivatives. Okay, and we know how to compute this, and the cost is again 2 PDE solves in this context. Okay, so there's some challenges here, because doing this, hyperbolic equations have shocks, and there's all kind of technical issues to make this actually well defined, and to make it meaningful, to make these computations actually converge in a sense when you refine the mesh. This is just saying that if we have these gradients, if we go down this thing, the events become more extreme, and this just gives you the number of iterations here for these events. So the main thing is here, the events become more extreme, meaning the event becomes more unlikely. Okay, this one says a very low probability, right? But the nice news is solving the optimization problem that goes with it. You can do this pretty much a constant number of iterations. So this doesn't degrade as you go more extreme, which is nice, right? Because the big danger is that these problems actually start becoming harder and harder as you go to lower probability events. And that doesn't seem to be the case here, as you can see from the number of iterations to solve these optimization problems. I've mentioned we need second derivatives. And just briefly, so we compute second derivatives, directional second derivatives. We know how to do this, and we don't need to assemble the whole second derivative matrix. We only need to apply it in certain directions and explore it. We find the dominating eigenvalues because they contribute to this correction factor in the probability. The way we do this, we apply this matrix to random vectors, and then we use ideas from randomized SVD, and that usually means that you can compute this correction factor by just a handful of applies of this matrix. So for this case, so only the first 5 or 6 eigenvalues of this matrix that's involving the second derivative of f plus the covariance of the underlying probability. So some mix of those two, and you only need to compute like the first or 6 eigenvalues, and they basically tell you everything you need, all the correction. Then you already have like 4 or 5 digits, so you're okay. So this is this local geometry information, and it doesn't seem to be, so that gives you hope that you can actually do this in very high dimensions as well, right? Because it seems that only for this problem, right, only the first 5 or 7 modes contribute to this correction term. So that's good news. So it doesn't depend on the dimension of your discretization, at least. Okay, that's just a summary of other challenges. So these equations are hyperbolic and can have shocks. And in the case when you have shocks in the context of computing gradients with adjoints, you have to be quite careful. And what we do is actually we use artificial viscosity to not allow actually shocks. Okay, there's and there are proofs for actually slightly simpler models from the shallow water equations that you can rigorously prove that gives you in the limit correct gradients. So there's this question about how to discretize the shallow water equation. I didn't talk too much about it, but basically here we just use a discontinuous Galerkin scheme in space and then Runge-Kutta scheme in time. And other people have looked into this. And then there's a bunch of challenges I also didn't really talk about in PDE-constrained optimization, because it's an optimization subject to a hyperbolic equation, and that's not what the PDE-constrained optimization community usually looks at. So so there is a bunch of challenges here because this is kind of a somewhat new structure. And the thing I also didn't talk about it also leads to this question of time optimal control, because this objective had if you remember, had a max term in there. So if you want to solve this exactly, you end up with time optimal control. Anyways, there's a bunch of challenges in these directions. Main takeaways, I already showed them to you basically. So I won't repeat that. And yes, our models are very simplistic. We're at the moment trying to do two-dimensional shallow water equations, but then everything becomes more interesting. There's more interaction with the shore. It's going to be much more. I think it's going to be more complex and more interesting. You can use some of these ideas to actually influence the probability of occurrence of extreme event. And most of the stuff is actually in this preprint here, most of the stuff I showed you. And this is just some literature, and the summaries I was trying to argue rigorously or somewhat rigorously connection between optimization, PDE-constrained optimization, and extreme and low probabilities, extreme event probabilities. And I was using it to say something about the likelihood, to say something in the context of tsunamis governed by the 1D shallow water equations. And that's some of the literature I've used. Thank you.
Thank you very much, Georg, for very nice talk. We have a few minutes for questions. Tong has his hand raised. Please go ahead.
So I asked the question, is that okay, Nicholas?
Yes, yes, yes.
Okay, so very nice presentation. So I had a question about in the case, so if I understand you correctly, you try to optimize just one single point on the boundary, right, which is called beta or theta star, and try to yield that at paraboloid to approximate that and try to approximate the boundary using parabolic in high dimension. Is that right?
Yes, and yes, yeah, I think it's right. And it's all working right in the limit when this thing slips further out, right? When it's in the limit of unlikely events, yeah. Then you can say something about how accurate it is.
Right. Yeah. It really depends on what kind of shape is the boundary omega z, right? So in the case of omega z is not a continuous set, but it's a disconnected set. For example, if you had a different subset in the space of theta, and then it would be really difficult right. Yeah,
exactly.
So
yes.
my question is, when omega z is a set of disconnected region, how would you handle that case?
I might not be able to handle that case. So the truth is, right, there is some regularity assumptions built in the assumption I quickly summarized. It's true, right? If this extreme event set looks very crazy, right? If it could wrap around like this, right? And this could be the extreme event set, yeah? If it looks, then my assumptions are not working, right? Because I assume actually that this solution is unique, right? I can deal with, or if it kind of, if it looks like this, right? So that means it kind of has multiple points, right, that are important, right? So then this doesn't apply, right? But so just to give some, so if this F mapping would be linear, right? So if this has some linearity, then we know that this extreme event set actually looks like is actually a half space, right? So if it was linear, then it would be half space, and then this is very easy, right? Then I can actually compute the probability exactly analytically, and that's nice, fine. So to some extent, right? I want to be clear about this. I need smoothness and certain regularity that you can find cases where you don't have that. where then you can't, where you basically lose this identity that you have a unique solution here, and then you can't do this. If you have multiple disconnected set in high dimensions, I don't know how to do this. So this requires a certain amount of niceness of the mapping F. And yeah, niceness and regularity of the mapping F. So I obviously need second derivatives to do this local approximation. And if it's crazy nonlinear, my methods won't work.
Okay, thank you very much. Yeah.
Any other questions?
I have a question. So this is Chen. In your initial setup, you just assume the B naught. B naught is a Gaussian distribution. So I'm thinking about for the real case, actually, when the big earthquakes occurred in the bottom of ocean, there can be like a seismometers to measure the elastic waves. So with that constraint, I mean, if the B naught is better constrained by the data, I mean, how does that like change the geometry of the objective function? I mean, for the reality, actually, the B naught can be constrained by the seismic data. So if the B naught conditioned on some data.
So I think you're right, and that's kind of what we're trying to do in this more physics thing, right? So it's true. When the actual event happens, then you can actually, if you're fast enough and you have sensors there, right, you can actually measure the up and down lift, right, and then you might be able to really say immediately what happened there. But my perspective is here, right? I'm just trying to estimate probabilities, so I find a model of the distribution of the up and down lifts, right? And actually, I didn't talk too much about this, but what we actually do is we actually model, that's what the seismic people I think do, that we model slips in this region in the rock underneath the ocean floor, right? So there are slips because this is what actually happens, right? And then these slips, the distress slips due to stress release, right? You observe them. So this is usually elastic material, right? So you observe them as like some up and down lift here on the ocean floor, right? And that map there's a model called Ricardo model for this thing. And yeah, so we just try to model that distribution and then say something about the probabilities. If you actually, in the event that this happens and you get data, then you can actually probably, if you have measurements, you could, I mean, that's interesting, right? You could still model that distribution based on historic data and everything you know, right? And then if you have real-time measurements of the up and down lift, you could then say, okay, so you could constrain that distribution by saying kind of an inference problem. You could say, okay, so now I have these observations. That means the event was most likely one of these. So it will be a much narrower set of possibilities, right? And then you could update your predictions based on that. I think that would be interesting to do. I agree. But at this point, right, our setting is.
Yeah, thank you. I think it's super interesting. And the other kind of related question is sometimes if we really know the slip distribution, just especially if we have the seismometer on the bottom of the ocean, I mean, if the B naught is well constrained, actually, the problem is not an extreme event because if the B naught is well constrained, actually, the FD actually is also well constrained. Then it's sometimes it's not an extreme event.
Then it's Oh, you see. I mean, if it's well constrained, but then you just need to run a simulation, right? Because if you know exactly the ocean, then you just need to simulate it, right? And you can compute it, right? So then it's kind of, then that's true if you know what happened. But usually, I think what happens is there's an event, right? And then months after the events, seismologists so actually get estimates for the slip that occurred in these regions, right? But that's usually done after the fact, as far as I know. I'm not a seismologist, but I'm. So, but I agree, right? I see. Once it happens, right, then it's not an extreme event. I agree with that. Yes.
Yeah. And the other fun thing is just sometimes the seismologists, when they have the observation, I mean, because there will maybe the fracture on the bottom of the ocean, but the fault may not always be up and down. It may be like in the horizontal. So
Yes.
we call that a mechanism. So
Yes.
it's kind of a interesting thing is sometimes it's an extreme event. I mean, if it's kind of sometimes it's extreme events. Sometimes it's not. I mean, just
I see the point. Yeah. So
yeah.
I agree. So first, I mean, yeah, there's not only horizontal shift. Actually, for this map here, I was showing I cut away a part that here they cut away the part that shows the up, not up and down, but the horizontal shift. But I think it's dominated. The effect is usually dominated by that up and down lift, as far as I understand. But I agree, right? So in some extent, it's the extremeness is a little bit maybe strange in this context. So in some sense, you can also just think of this as a forward propagation of uncertainty, right? You have some high dimensional parameter field, you push it to F, and you propagate it forward. And instead of being interested in the whole distribution, you're only interested in the part that is in the tail. So yeah, I agree that once you know that what happened, then the extremeness doesn't really make that much sense.
That's a super interesting question. I mean, sometimes it's an extreme event, but sometimes it's not. I mean, with additional like observation support. So yeah, I think it's a fun. Thank you.
Thanks.
Any other questions? So just for the physicists among us, the extreme event theory looks to me like a generalization of what people refer to as transition state theory. Is that true?
So I think I'm not sure. I'm not sure if I'm not sure, but I think there's these two notions. I think actually Tsunamis has some. He distinguishes between sometimes between something where the extremeness is caused by the dynamics of the forward model, right? By something, you trigger something, and then the dynamics starts to kind of generate that extreme event. This is, at least for this example, that's not the case here. The dynamics is not very nonlinear, right? It's not. It's somewhat reasonable. It's not. The extremeness is not caused by something by seed, and then it grows over time, and then it leads to something extreme. For this thing, that's not it, right? Because the extremeness is mostly governed by the complexity of the parameter, the underlying distribution for theta, and then the forward model is not is the Shell-Water equation. In this case, it's a nonlinear problem. It can have some complicated effect, but it doesn't have this effect that something could grow that's over time and lead to something chaotic. I think this is what you mean when you say transition. And so there's these two classes, right? One, the extremeness is really caused by the dynamics, and the other one, I think it's more caused by the dynamics is more harmless, but it's more caused by the probability by the distribution of the parameters. And so somehow they're a little bit different. Sometimes people call one extreme and the other one rare events. And I'm a little bit confused still about if it's necessary or useful to distinguish them. But I think it's more the case where the dynamics is relatively easy or easy, but it's not as nonlinear as you would do when you do turbulence, for instance, where a tiny thing can lead to huge effect, right? I think that's not the case. That's not, my forward model doesn't do that here.
Okay. Thank you very much.
I'm not sure if that answered the question, but
it's certainly something to read more about. Great. Way past time. So let's thank Georg again for a very nice talk. Thank you very much.
Thanks everybody for coming.
Yes.